Good morning, all of the participants. So, on behalf of Evolution and Health Effects Research Center, I would like to welcome you all to the special lecture today on the topic of learning from data analysis of evolution. So, it is my pleasure to introduce you Professor Don McNeil, who will give the lecture today. So normally I call him Ajahn. In Thai, Ajahn is mean lecturer or teacher. So before beginning of the lecture, let me have a brief introduction to Ajahn Don. Ajahn Don got PhD in statistics at the Australian National University, and he used to work as associate professor at Princeton University in USA for about more than 10 years. And he moved to work at McNeil University, Australia as a full professor for about 20 years until retired. And he got publication and had written many books. For example, Modern Statistics, A Graphical Introduction, Interactive Data Analysis, and the most famous one is Epidemiological Research Methods. So this book is the best one that I generally use this book. And Ajahn Don first came to Thailand in year 1987 to run a short course in applied statistics at Prince of Songkla University in Hat Yai campus. And later he came to Pattani campus and held Faculty of Science and Technology to set up master degree in year 1995 and PhD program in research methodology in year 2005. As Ajahn Don has a lot of experience in data analysis, so the main focus of this program is learning data and add the value to the data by applying the appropriate statistical methods. So currently, there are more than 85 master degree students and 46 PhD students graduated from this program. So Ajahn Don have done a lot for Thailand, and he has a lot of students. I think more than 300 students in Thailand. He produced a lot of postgraduate students. Now, is this the time? I would like you all to welcome Ajahn Don for the talk.
Okay, I'm still not, can I talk now?
Yes, Ajahn. Yes.
You can hear me. Right. Okay. I'm very happy. Thanks very much for saying those nice things. I've enjoyed working very much with you in Thailand, and I hope to continue doing so. But maybe I won't be able to get there for a while because of COVID. And I'm very grateful to Professor Pirapong for organising this event. And I'm looking forward to doing some research with him too, and his colleagues in the Faculty of Engineering in Hat Yai. We've also got an engineering faculty now at Macquarie University, and yesterday I had lunch with the dean there, and he's very interested also in what we're doing, and he doesn't agree with me on a lot of my views, but I had a good discussion with him yesterday, and maybe he'll come around. We like to drink coffee together. Okay, well, what I'm going to, I've prepared just a small number of slides, and I thought I might just go through them, but I also want to show you how we do things. I don't want to just show you the slides, and you should be able to actually do the same. The data that we'll start with is the data that you got from the Department of Pollution Control in the Thai government, and I think we'll start with that. I'm not going to use all of that because there's a lot of data there, and a lot of it's missing too. Okay, so let me just see if I can find the slides. I've got them here somewhere. I've just got to find everything here. Right, here we go. Now, I need to share something, don't I? Or can I, let me just see where I am. Okay, I don't need that open. Okay.
Yeah, you can go ahead and share it.
All right, so I will share now. I'm just trying to find the button that does that. It's gone. There was a share screen here. Where is it? It's not this thing, is it? No.
Agenda, move the mouse around and then the menu will appear.
Yeah, the menu sort of disappeared. I'm not sure where it is. Maybe, oh, it's gone. Oh, wait a minute. I think it's on this other, I've got two computers here.
Yes, you use two screens, Ajahn. You have to.
And I still can't find that share. It was there a minute ago, and it's gone. Yeah.
I think it is the button at the bottom of the screen around the middle of the screen.
Yeah, I'm looking for it.
Can you see it?
Well, there's one that's got a camera, a picture of a camera. It's just gone. I might have to get Rogan again because he's more familiar with this. It's definitely not here. Wait a minute. Here it is. Okay, it's coming. Funny how they disappear. Now I'm going to click on that. Okay, now I have to do something else, don't I? Is that right?
Yes. Yes.
Do I click on screen? No.
Yeah. You can click on the screen and then share.
Well, I did that. Now there's still something more I've got to do, isn't there? Sorry to be. Oh, there's a button that says share. I click on that. Okay. Now can you see the screen I've got?
Yes.
Okay. I've got some files there. And one of the files should be called, where is it? It should be a PowerPoint slide because I created it this morning. Zoom presentation 3, that's it. Okay, we've got it. Right, now, can you see that? Now we go back to the start. Okay, this is the first slide. This is the sort of cover. Can you see that?
Yes, we can see that.
Right, okay. So now we're in business. So I'm going to spend a bit of time on the air pollution from the Thai weather stations. And I'm going to talk about missing data because there's a lot of missing data. And that's, I see Ruth there. Hello, Ruth.
Hi, สวัสดีค่ะอาจารย์ Don.
Good to see you. Right.
Good to see you.
We're going to talk about histograms and QQ plots. I think everybody knows about histograms. Even people who know nothing about statistics know about histograms. QQ plots might not be so well known. They're important, very important. So we're going to spend a little bit of time on them, but they're very simple too. Ajahn Virasak actually has an even better graph than a QQ plot, but I'm not going to use that today. But then I'm going to talk about the need for transformation of data. This is something I learned when I went to Princeton. When I went to Princeton, there was a guy there, and I didn't know about him before, and he just changed my whole life. His name is John Tukey, and I was his colleague in the statistics department at Princeton. And you know, he was just the person I learnt the most from. And I'm going to talk about some of his ideas today. And they're very simple ideas. The trouble is that he died in about 15 years, 20 years ago, and he still has, and of course, when you die, sometimes what you've done doesn't follow you so well, you know, you're not as famous, although he is still pretty famous, really. But anyway, I'm going to talk about some of his things. And I'm going to talk about box plots. I don't think he did
Don,
really have,
could you make the PowerPoint to be full screen?
full screen, okay.
Yeah. Thank
Is
you.
that it?
Yes,
Right.
yes.
Thank you.
Right, now,
But
one of, yeah,
Don
anything else?
is like a
Caption.
yeah, it appear like it's not full screen, but it's like the one that you present.
Oh, I see.
Ajahn Don, go to display setting and swap. Choose the menu swap.
On the top, Ajahn, display
Ajahn.
setting.
Display
On the top, a bit
Display.
to the further right. The next one.
The next one,
Yes.
yes.
The display
Middle.
setting.
Settings.
Display setting. In the middle one, middle menu. Display setting.
Oh, yes, I see
Yeah,
that.
and then click on that
Map.
and
Yeah.
swap presenter.
Yes.
The first one.
Yep,
Yes.
that one.
Okay, good.
That's what you wanted.
Yes.
Is that right now?
Yes.
You don't sound convinced.
Yes, Ajahn.
It's okay now, is it?
Yes.
Can I continue?
Yes.
All right. Okay, so I'm just saying that one of the things that Tukey invented was box plots. And I don't, if you look him up on Google or somewhere, it might say that that's one of his, that he's famous for that. But really, I think he wouldn't be happy to be famous for box plots because that's just a small thing compared with all the things he invented. Another thing was that he invented was, he had a lot to do with the fast Fourier transform method and things like that. He did a lot of work in time series. Anyway, so we're going to talk about box plots. And I'm then going to talk about time series plots. And when I've done all that for the air pollution data, I then want to talk about a couple of other data sets, including the hospital visit costs. We've already looked at that, and a lot of you, and in fact, June studied that in her thesis, and she got a publication out of that, quite a good publication. And I think that's a very important paper. It's probably one of the best papers to have been written by anybody in Thailand, the best science and medicine paper. Now, of course, it'll probably take a few years before that becomes obvious to people, but that's what happens when you do something new. It sometimes takes quite a while before it gets, it makes you famous. So I supervised, and of course, Apirity you had a lot to do with that too. Anyway, well, I'd like to just talk about that because it's quite relevant to one of what we're doing today on the air pollution. And the other thing I want to talk a bit about is data science analytics, including neural networks and other machine learning methods, random forest, because that comes into it too. And I think we can't ignore that nowadays because everybody thinks it's really important. And then finally, I've got some new maps that I can show you that are actually better than I thought. The ones that Ratikan and I were using for the global warming maps were pretty good, but I think these ones that I'm going to show today are better and possibly quite new, although there's really nothing new under the sun. Anyway, so let's get started. Okay, now this is the first slide really. The slides are numbered at the bottom, the numbers. So I'm happy to send this to everyone. It's just a short one, or you can just take pictures of it. There's nothing much there. Right, so let's just go over the data. The data consists of hourly data on concentrations of 7 pollution variables. There are others, things like methane, that are not included there, but these are the sort of standard ones that everybody uses. And you'll notice that carbon dioxide is not there. Well, I don't think many people would really consider that a pollutant, because carbon dioxide is absolutely essential to life on the planet. Plants cannot grow without carbon dioxide, but carbon monoxide is considered a pollution variable for various reasons, and you can look all these up. Ozone is another one, but it's a bit different from all the others. And then the sulfur dioxide, nitrogen dioxide, and other nitric oxides. And then there's the 2 particulate variables. These are small particles that get in the air and cause serious health problems. And the worst one is PM 2.5, which is the smaller one. Now, these data were collected at more than 32 weather stations in Thailand, but these are the ones that I think you got the purity from the Thai Pollution Control Department, so you could use them with the graduate students in our research methodology and data analytics program. Now, I'm going to be using R because I think R is really the best and in many ways the simplest program to use for data. That not everybody agrees with that, but you'll see it works pretty well. The problem is that a lot of the data are missing. Suppose you had data for every hour of the day and each year for all variables in every station. The total sample size would be 47 million. That's how many numbers we should have. You can work that out. Just multiply 24 by the average number of days in a year, which is 365.25. And there were 24 years of data. I think some were missing, all were missing at the beginning and maybe a few at the end, but and then 7 variables and 32 stations. If you multiply all those together, you get 47,126,016. But then when you look at the data, and I checked this, I wrote a little program that counts them all. There's only half, just under half, that the rest of them are not there, they're missing. It's in a database where they could be there. The indexes for them are there, but the data are not there. So, and if you look at the percentages are around 50% for 6 of them, but for one of them, the last one, which is in many ways the most important one in terms of danger to your health, PM 2.5, that's under 5% of the data are there. And that's because in most stations, they didn't really start recording them until quite recently, the last few years. So what we're going to do today is just look at 5 stations with the least amount of missing data. They are Hat Yai, Rayong, Din Dang in downtown. That's a sub-district, I think, isn't it? In downtown, it's right in the middle of Bangkok. Very busy, a lot of traffic there. Lampang and up north and Chiang Mai. Okay, so we'll look at them. Now, I'm going to start with the histograms. And I can go through, if there's time, I'll go through and show you a program that does that. We might have a little break and I'll just run that just to show you how it works in R. And the programs are really quite simple. We don't use any fancy packages or anything. It's all done just by using very simple basic commands in R. So we're going to first make graphs of frequency distribution. Now, here are the histograms of each of the 7 variables, and we just do that just using the hist, H-I-S-T function in R, and that's what they look like. Now, we also put some labels on them, telling us the number of observations, the percentage missing. Now, this is for all of them, not just for one station, but for all 5 of the stations in our sample. And so you can see very clearly now, and also it shows you the number of zeros. They've all got zeros except for the very last one, the PM 2.5. And also the PM10 has only got a very small number of zeros for the hourly data. Now we're going to get to some assumptions that statisticians make. They assume that statistics is largely uses the normal distribution as its model. And there's a reason for that, because the normal distribution, there is a theorem in statistics called the central limit theorem, which simply means that when you take some numbers and work out the average of the numbers approaches a normal distribution as the sample size increases. There are some little assumptions you need to make, like that the variance is finite, and there's not too much correlation, but that's basically how the normal distribution arises and why it's important, because you tend to look at averages in order to improve your accuracy when you do analysis. Now we get to these quantile or QQ plots, because they show how closely data are fitted by a normal distribution. So if you want to know whether your data are approximately normal or not, or nowhere near normal, you can just use the QQ plot. And there's a very simple function in R called QQ norm that just does that. And then you can use another little function called QQ line, which fits a line and on the same graph. And here I've made it red. And that line, if the data are normal, the QQ plot curve, and it basically, what it does is it plots the quantiles of the data against the theoretical quantiles of the normal distribution, which you can work out very simply. And they never change. See, they're all the same. Whereas the quantiles of carbon monoxide, well, you can see them there. Here they are. The quantile that I put the numbers on the horizontal axis here. When you make a histogram, you have the values of the data, and on the perpendicular axis up there, you have the frequencies going up. But here you have the data, the values of the data on the QQ plot. You have the values of the data on the vertical axis, and you have the theoretical quantiles of a standardized normal distribution that has mean 0 and variance 1 on the horizontal axis. Well, you can see that none of them are really any close at all. They might have a period where they follow the straight line in the middle usually, but then they get away from it. And they're all getting away from it by going up, away, and at the bottom, well, they tend to follow it down lower. But anyway, well, so that means, and when you get a curve like that, it means that the data are heavily skewed to the right. That's what happens with a lot of data nowadays. Not only pollution data like this, but data in biology generally, organism counts, infections of disease, the numbers go up very quickly when the disease gets out of control. And financial data, the same. Money, the distribution of money is like that. And you have to take logarithms in order to get a better fit. So that's the next thing we're going to do. We're going to use scaled logarithms to try and improve the QQ plot. And one of the problems with these data, and a lot of data, is that if they contain zero, they have to be non-negative. You can't have a negative value of a pollution count or a number of organisms or money, but they can be zero. And you can't take the log of zero. So, but what you can do is you can add 1 to the number you've got and then take the logarithm. And the advantage of doing that is that that means that when you take the log of 1 plus the number, if the number is 0, the log of that is 0. So so it still starts off with the right value. But there's another problem here. If these were just counts, like numbers 0, 1, 2, 3, then that might be okay, just to take the log of 1 plus that number. But when they're concentrations or amounts of money or something like that, you can, it depends on what unit you use. If, like in finance, if you're using baht, you might get one answer, but if you're using the same amount in dollars, US dollars say, you'll get a different answer, and they can't both be right. So then you have to have a way of scaling them so that you get the best, and you can choose that in order to get the best fit of the normal distribution. So that's what we've done here. We've used the first panel there, the upper panel of those QQ plots is the same as on the first slide that I showed you before. But now the lower panel is where and that's just taking the log, taking the QQ plot without any transformation. The one below is taking the log, but choosing another number, and for carbon monoxide is 10. So we multiply the carbon dioxide levels, concentrations by 10, whatever they are, they're actually parts per million. And then we add 1, and then we take the log. And when we do that, we get a plot that actually follows the curve pretty well. You can see that. It's got a shelf at the bottom, and all those values at the bottom are the zeros. So if you've got a lot of zeros, you've got a flat step at the bottom, but then after that, it takes off and it follows a nice red line that's been covered up a bit there, and that works pretty well. And if you look at ozone, you get a similar result, but this time, instead of multiplying the level by 10, you actually have to divide it by 20. Now, why do you have to do that? Well, for a start, the ozone measures that we get from the people giving us the data are parts per billion now, not parts per million. It's customary to measure ozone in parts per billion because it doesn't occur as much as in the atmosphere as carbon monoxide. So parts per billion is the unit they use there. And that already means that you have to change the constant in the scale. But then you get a fairly good fit. Now, when we look at sulfur dioxide, we multiply by 20, and that's also parts per billion. But now we get not such a good fit. Not only is it there are a lot of zeros at the bottom that give it that shelf, but then it still gets away, and there doesn't seem to be anything easy we can do to make it follow, to make it fit. And if we tried to make it fit, we'd probably make things worse in a sense, because there might be a reason why it doesn't fit for higher values, and that probably means something. And you'll see, and when, for example, when we look at June's hospital cost data, it turns out that there are some very high values, unusually high values, corresponding to medical procedures that cost a lot, that like ventilators and things like that are very expensive, and they probably should be separated out. Sometimes you've got two, it's not, when you take a sample, it might be better if you split it up into two different, essentially different parts, rather than try and fit the same distribution, the whole thing. So we're not, it doesn't necessarily follow that everything, if you put everything together, it should be normal. So that gives us information. You see, what we're trying to do here is to learn from the data, because the data might tell us something that we don't already know or we've overlooked. And that's one of the reasons why we have to know something about the subject matter. Well, that's hard for a pure statistician or data analyst to do, or a computer scientist, or whoever's doing fitting the model. But that's why you have to have a team, where you have some people in the team who know a lot more about the subject matter than the statistician or computer scientist. Anyway, just to move on, you can see now that, again, for nitrogen dioxide, it fits pretty well, but then the opposite thing happens with large values. It slows down at the top, and there's probably a reason for that too. There could be some ceiling effect that means that it can't go up beyond a certain level for some reason. And again, the same thing is happening with other oxides, but they're a bit more complicated, because some of them are starting to go up faster, but then they reach the ceiling. Now, when we look at the two particulates, we see that it's not too bad there. It's we've got the smaller values, but they're probably there because you couldn't measure such a small quantity accurately. That's probably, if you had a better means of measuring it, you might be able to get the smaller values, but maybe your measuring equipment can't cope with them. And when we look at the smaller particles, that similar things happen. We've got a couple of numbers down here, just a few numbers that are 0.1, and I think actually that happened because I actually put some values equal to 0.1 that were 0 in the database. Why did I do that? We'll come to that later. But I did something to the data. I didn't allow zeros in the data. I think the reason was that it was better just to take, you see, I've just taken the log here because I've got rid of the zeros pretty much. When we looked at them, we found there were only a very small number of zeros for the larger particulates, and there weren't any for the smaller ones. Okay, well, let's move on. Now we're going to look at box plots. I just looked up box plot on the internet, and I just found this this guy. His name's Michael. He's given some. He's got a web page that he says you can read it all in 7 minutes. He gives a little but he's pretty accurate. He uses something called the interquartile range. You see, here's the box plot is constructed by taking the lower quartile, the median, and the upper quartile. That's the starting point. And then you put a box around that, and you put a slice down the middle where the median is, and then that range is called the interquartile range. Tukey had a different name for everything, and he called it the mid-spread. And then you can look at you then construct a minimum, a sort of a minimum that you think is reasonable if it were perhaps a normal distribution or something like that. But the way Tukey did it, well, I think he took the lower quartile and then he subtracted 1.5 times the interquartile range. He did the same thing at the other end. And then anything outside that he called an outlier. And so that's what it is. And that's what R uses to do it. You can give it, you can change it and put more options in, but now when you look at the data for HAT-YI, for the carbon monoxide, using that data transformation we got from the QQ plot, that's what they look like. And the advantage of a box plot is that you can show how a variable changes with respect to time or location or something else. You could have different people doing different things, and they could be a sample, and you might have repeated measurements on each one of them, or they might be in a team doing a clinical trial at a place, and you can put, if you want to put all the data together on one plot, that's a good way to do it, because the box plots are one-dimensional objects, whereas a histogram is a two-dimensional object. They fit better, and you can have a lot of them. Well, you can see here that there's a bit of a looking at hour after midnight, hour of the day, which is hourly data. We have that in the database, and there are 24 hours in the day, starting with the first hour after midnight. And then when we get up to 8 a.m., you see the distribution goes up. And it actually goes up quite a lot, because remember, this is a log scale we've got on the vertical axis. But we do it that way in order to make things more even, make them follow a normal distribution better, which is more homogeneous. But then you see we've got a lot of outliers. These are fairly big samples. So you've got a lot of outliers at the top, but not many at the bottom. And so there's still some skewness left, even when and if you go back and look at the curve, you see, it's hard to see that, but that's what happened. Well, that was what happened in HAT-YI anyway. So you get all these, this didn't show up so well on the QQ plot. So the box plot tends to find that out by looking at the outliers. And the reason why you have this bump at 8 a.m. is probably because that's when people start driving to work. They're asleep before that. And then it flattens out, and then it goes up again in the evening when they start driving around or doing things later on. So that can be all explained. Okay. Well, now we're going to do that for every station and every variable. And you can see that when I did this, I got a bit of a shock. I was thinking of doing it another way, using some kind of scatter plot of the medians or something. But I think the box plot does a very good job of showing. It's quite pretty, really. You could make a carpet or a dress or something out of it. But you can see it does actually tell you the pattern in the data very well. It gives you the outliers, it gives you the center where the mean or median is moving, and you can see the differences. You can see, for example, that you can see immediately that ozone has a different pattern to the others because it goes up in the middle. And that's because ozone is related to the sun, and the heat increases the amount of ozone, so in the middle of the day when it's hotter, the level of ozone. So you see, we're finding out things by making these graphs, whereas the other variables are all have a bimodal. They have a local maximum around 8 o'clock, and then another one in the afternoon or evening, and some more so than others. You can see that Dindang has somewhat higher values of a lot of them. You see here, particularly nitrogen oxide, nitrogen dioxide, and nitrous. Dindang is higher than the others, quite a lot higher. And so you can see some of the patterns, and you can think, well, why is that? But it just tells you something. Okay, let's move to the next one. I'm now going to look at daily averages rather than hourly values. And the reason for doing this is that I want to really focus on the bigger picture, not just looking at the variation throughout the day, which I think everybody knows about and is important, but it's more important to see overall whether it's increasing over time. There could be a day of week effect. It's probably more likely that there'll be something different at the weekend. That might be important too. But maybe the more important one is the season of the year effect, because there are seasonal factors that we need to know about. And of course, there's also the trend, the long-term trend over time. So in order to get a handle on these things, we need to really take out the variation, the seasonal. When I'm using the term season, it could be part of the day, part of the week, or part of the year. Seasonal usually means how things vary over the year, where we have a season. So we have the 4 seasons. So I'm going to first look at daily, and that will reduce the data a lot, and it might even clean the data to some extent. Let's see what happens. But when we do that, now we probably should. I should have been able to show the 2 on the 1. I'm not sure that I've done that, have I? Oh well, I can. Don't worry about the histograms so much. You can see that these are the QQ plots now of the daily averages. So each value in here is not just the value for a single hour, but the average of the values for the whole day, the average. And now if we can compare that with the well, I think you'd have to go back. Well, I thought I'd done that. If we just go back quickly, you'll see they are a little bit different. I thought I had another graph here, but maybe not. No, okay. All right. Okay, I think there's a graph missing. But you can see here that we now look at the, yeah, you remember the PM 2.5 had a fairly big wiggle at the bottom. Let me just go back and show you that. You see that? There's the hourly data. Now when we go to the daily data, you see it's almost perfect. It's perfectly normal just by taking logs. And of course, when you take the log without adding the 1, there's no other constant. You don't have to scale it at all. It could be parts per million or parts per billion or and these are micrograms per cubic millimeter, per cubic meter. That's the unit for both of those. And here for the larger particulates, there's still the funny things happening for lower values, which is probably something to do with your measuring device. Okay, well now I'm now going to move on and look at week of the year seasonal pattern. So I've now got data by taking the average of all the values in 1 week. And the way we've done that is because there's not exactly 52 weeks in a year, it also depends on whether it's a leap year or not. In the ordinary year, there's 52 weeks plus 1 day, I think. Yeah, is that right? There are 52 weeks and there's a day, an extra day. And then so that when you go to the next year, the same date is 1 day of the week later or earlier. Well, now, and it's a leap year, you've got 2 extra days so what we did there, we still kept it at 52 weeks by saying the first week is always 8 days. We won't count January the 1st. Well, we'll count it, but we'll take the average for the 8 days rather than for the 7 days. And then if it's a leap year, we'll do the same for the last week in the year. We'll make December the 31st. We'll throw that in as well, and we've got 8 days at the end. And that way we get exactly 52 so-called weeks. It's just that a couple of them are slightly different lengths. Well, when we do that, there's the box plot for HatYai, and this is for micrograms. This is for the PM 2.5 micrograms per cubic meter, the smaller particles. Okay, and now when we look at the plots for time, now these are still box plots. You see, it's hard to, they just look like scatter plots. So I think the box plot's a pretty useful device because it shows you fairly clearly what's going on with the data in terms of the seasonal pattern. Well, you can see, for example, for din dang for sulfur dioxide, it's jumping around quite a lot. Why is that? It's just each time we look at a graph, it raises a question that makes us think about why. That's the whole idea of learning from data. You see the data, you get the information, but it doesn't tell you why. It just shows it to you. And that's good because that forces you. And then you have to think about that. And if you've got somebody in your team who knows about the subject matter, they will quite likely come up with the answer to the why question. Whereas it's very hard for the analyst who doesn't know so much about the subject matter to do that. The analyst can write the program, do the analysis, do all that. They're a computer scientist type person. And they can look at the evidence. They can say, oh, well, that looks a bit funny, but the sample's not big enough. There's not enough evidence there, you see. Statisticians can get p-values, probability values. They can do ANOVAs and things. And they're the ones who learn how to do that. Everybody else finds it horribly boring and difficult, and they don't want their students to have to waste their time learning that stuff. I know doctors are like that. But that's why you have biostatisticians and statisticians who are epidemiologists too, who know a bit about the subject matter, but not as much as a doctor. Well, anyway, I just thought I'd show you those curves. Okay, let's move on. Now we get to time series plots. The time series plot is what we're really interested in. The seasonal pattern is important. You need to know about that, and you can't ignore it. And now we get to the time series plot, because the time series plot shows you how things are changing over time, and you need, because we've fitted a normal, because we've tried to make a transformation that fits a normal distribution and hopefully has a homogeneity that produces data that are homogeneous normally. I mean, you will get departures from that, and the departures could be real or they could be mistakes. You can see here, Ding Dang, there's a little trail there, values that were a bit higher. So there's 3 weeks there. These are weekly. We're looking at weekly data now. So there's about 3 weeks there in a row where the data went up or down, or went up and maybe came down again slightly, but jumped around up in the sky, so to speak. But the rest of it was in a more a narrower band. Now here you see this is important. You can see that sulfur dioxide has gone down very steadily from a quite higher value, 40 units per parts per billion, way down to close to 0. That's about 1 or 2 over the period of 24 years. Now, why is that? How did that happen? It didn't happen in other places. It didn't happen in Hat Yai, but it was already much lower in Hat Yai to start with. Is there anywhere else where it was high? And that's the high. Well, there's a odd value here for Rayong, but that might be just could be a mistake, or it could be some reason. So anyway, these are, and now we can look at other places and see we can make the same curve. Even though we've got a lot of missing data, we've been able to see get the information out of the data. Now you can see that for the small particulates, and these are the important ones for environmental health problems, we didn't start getting for these 5, and these are the 5 stations that had the most of these data. I think if you there were at Yai, there were 80% of the data were missing, but there were, and most of the other stations, more than 80% was missing. For a lot of them, there were 99% missing. Rayong, I think, did better. There were only about 30% missing, or 35% for Rayong, and the others were closer to 80%. Not quite so many here. Maybe there's a big gap here. Okay, so what you would do now, the question is, what do you do next? Well, what we've done here, we've kind of cleaned the data sufficient. The data were already not too bad. They were just missing, I think. but we've now put them in a form in which you can do the next step. And the next step is forecasting. And that's a big issue, and I haven't got time to talk much about that today, but I understand that that's what we're going to be doing in my Zooms for the graduate students in your program, Apirity. Is that right? Forecasting. I've got some ideas on that. I've got some quite good new ideas. They should be able to get lots of publications. What we're going to be doing is fitting spline functions. We're going to be looking at methods for comparing them with data science methods, for example. We're going to be doing a lot of we're going to be doing some empirical work. The problem with a lot of these time series is that, of course, you can't sample. You see, really, ordinary statistical analysis is easy because all you're doing is sampling from a population. The population could be huge, could be infinite even, and you just take a sample, and as long as your sample is unbiased, and there are ways you can guarantee that your sample will be unbiased, as long as you can sample from anywhere in that population, which you usually can because the data are cross-sectional data normally. But if the data are time series, you can't sample from the future. No way. So then you have to make a very big assumption. You have to assume that the process generating the data is the same in the future as it has been in the past. Now, for some situations, that's not a problem. For gravitational, for the movement of planets, moon and tide, things like tides, anything that depends on gravity is probably not going to change very much in the future. You can have terrible events like meteors crashing into a planet and making it go a different way, but that doesn't happen very often. And so usually in a lifetime of a person, there's not going to be any, that assumption is reasonable, that the process generating the data in the past hasn't changed. But there are situations where that doesn't happen. In finance, that can be a problem. And in now with climate, you see, that's another issue. Are things changing? Perhaps due to populations exploding. There are now 4 times as many people on this planet as there were when I was a little kid. That could make a difference. A factor of 4 increase in population might have had some effect on the climate, you see. It could have caused the temperature to go up, something like that. All right, well, we'll get into all that. And there's another issue, and that is that, and this works, if the structure may be the same in the future, but you can have correlation in time series data. It's called autocorrelation, and that can make a lot of difference. And you can get the wrong answer if you don't take account of correlation. I think people know about that. That's nothing new, and there are methods to deal with it. But you need to know about those methods. Now, I haven't considered that at all here. I've just shown you graphs of the data. Now, then we have to say, well, if the data were correlated, would these graphs, if the data were more correlated, would these graphs look different, you see? So but we can still use these graphs to address that issue. These graphs that I've shown you are the basic graphs. And that's all you need, see? It's not too complicated. It's very simple. So I've covered everything on the air pollution. Pirapong, are you disappointed that I didn't cover more? Pirapong, what do you think?
No, please go ahead. Very interesting.
Thank you. All right.
Yeah.
Well, I mean, I could have gone into more detail with fitting this spline functions and the forecasting and all that kind of stuff. In fact, we did that. We've already done that with these data. Purity, you might remember we fitted some spline functions, didn't we? And we forecast. But I thought this might be enough for this talk. And maybe we've still got most of the people, maybe people are still not too confused, right?
I can talk to Apiradi later, and maybe we can get help from you more.
If you want to.
Yeah.
All right. Well, now I am now going to go into a bit more detail, but I'm not going to use the air pollution data. Is that okay? Because I think
Yes,
the air
please.
pollution data's got some concerns that make it more difficult. There certainly is a lot of correlation, and there's a lot of missing data. So I'm now going to turn to a problem where there's no correlation and there's no missing data. So it's much simpler. But then that means we can focus on the issues of fitting the model that we're going to have to deal with the air pollution data. So in a sense, don't just go off now. Don't just ignore this, even if you're not interested in hospital costs. The method is the same. The method will be exactly the same for the air pollution data. It's just that this is a much simpler set of data. Okay, so I'll now, how's the time going? It's now, how much time have I used up? Have I used up an hour yet?
Yes, and you have 1 more hour.
Right, I've got another hour. Okay. Well, so what I'm going to do is now, some of you already know a lot about this because the article, we did present this at 2 years ago, nearly 2 years ago, at the workshop we ran in Suratani. And some of the people here today might have, I know actually went to that workshop. We had a lot of people there. I think there were 100 people there. And I think a period, June gave the talk together with one of the Arjans from Suratani campus, named, her name is Joy. She gave that. So what I'm going to do is I'm going to take those, I'm going to find that slide. I'll see if I can find it. It's on my computer again. I have to go back and get back to my computer. How can I do that? Now, I've lost my, where is it? Excuse me, I'll just have to put my glasses on so I can find things. I've lost that thing at the bottom that, have I? Or maybe I'll just close this. Yeah, okay. Now here's the hospital costs. So this is another set of slides. Now you can get this because if you go to the website, this is the talk we gave, and it was given by Apiridi June, who's here, who's finishing a PhD, hopefully very soon, and Joy Notaya. and she's in the she's in the Department of Economics, I think, in the Faculty of Liberal Arts and Management Sciences. Okay. Now, just to give you an idea of the background, this is actually quite an important problem, and the paper, June got the paper published in your local medical journal, at your Princess Onka Medical Journal. So there is a method for what happens, of course, is that the government provides money to public hospitals, and that the basis for giving the money is something like diagnosis-related groups, DRGs. It's not the only thing they use, but that's the basis for controlling hospital treatment costs. And now they have provided the Health Security Department in Thailand, which provides insurance cover for everybody, just about. There's different kinds of cover, and they supply the data to virtually to anybody who has a good reason for wanting it. And that means anybody, any doctor can get it, and if you know a doctor, or you can ask them. And so we managed to get some data from one of the hospitals in Suratani. I think it was the General Hospital, and we that database looks very clean, very good. But I think it's basically like a sausage machine. They take all the data, and of course there's always a lot of bad data and missing data and wrong data, but they tidy it up and they put it into a database, and the database is very clean. There are mistakes in it, I'm sure, but it's probably as good a hospital database as you'll find anywhere in the world, I would say. It's pretty good. Anyway, that's the theory behind it, and you can go and look at. There's been a lot of work on this, but I think everybody agrees that this DRG system is not perfect, but they still use it. Okay, so now they have databases for different kinds of diseases. The chronic disease is one, and anyway, that's so I'm now. We did some we ran an hour program to do it. That's what it looks like. Don't worry about it now. But basically, the data table is sampled from a much larger set, covering all visits over 12 years, from 2005 to 2016. Now, if you went and got the data now, you'd be able to get at least a couple more years of data. But this is what we got about 3 or 4 years ago. Now, to make it feasible, and we got people who came to the workshop that they could actually download this much smaller sample. It's still fairly big. It's 3,700 records. It's not tiny, but it's much smaller than the 200,000 records that June did the data analysis on. And her husband's a doctor too, so he was involved in the study. So now we look at a quantile plot. Okay, you now know what a quantile plot is, and that's the plot that we used for looking at the air pollution data. But now we've got the cost on them. Instead of having the concentration of the pollutant in the atmosphere, we have just the cost in baht. And you can see on this here, we've got a linear scale, and we do the QQ plot, and this is what we get. And you see, there's a very big outlier up there. It's actually a visit that cost more than 7 million baht for one patient. That's 350,000 Australian dollars. That's a lot. And it's probably wrong. But it's not an example of corruption, not necessarily, because it's just something could have, nobody, the money didn't go into anybody's pocket. It just meant that the hospital got a bit more money than maybe it should have for that, but it might have got less for something else, and it all averaged out. Okay, but you can see that big outlier there. But now when we take this transformation, we divide the cost by 100, which actually brings it into something a bit closer to $1. Well, it's a few dollars now, but it's, or a euro, it might be a euro or something like that. And then you add 1 and take the log. Well, now you see, you get a very good approximation to a normal distribution, except for that one outlier, which isn't really very big anymore, relatively. And then you've got this shelf at the bottom, which is what you usually get with data. And you can say, well, these are small things. So this is less than 800 baht, which is probably not too much. People can easily pay that. They don't really need to get insurance to cover that small amount. Okay, so that's what happens there. Now we looked at the abnormally high costs. Don't worry about that. That was just a reason. And if you talk to a doctor, they'll probably tell you, no, that must be wrong. That couldn't have happened. So it doesn't matter. But now we are going to simplify the analysis a bit. We're going to exclude visits with costs below 800 baht because that's sort of affordable in a sense. And we'll simplify the model just by taking logarithms, and then we just get a log linear model. We did something like that with the particulates in the air pollution. That it's always better to just take logs than to have to add 1 and take the log. Simpler, and you can then just use any software you want to do it. R does this really easily, but other software, it's a bit harder to just take. Excel can just show a plot on the log scale. Adding 1 is a bit more complicated if you're using Excel. So now you see the interesting thing is, and I didn't tell you this before, it's not the data that have to be normal. When you fit a regression model, or any model for that matter, it's the errors that should be normal, you see? Because when you fit a model, and as I said, even if you're not fitting a model, if you're just using some algorithm, like a machine learning algorithm, you are trying to separate the data into the part that contains the information, which you use for prediction and forecasting, and what's left over. And time series people call that the signal and the noise. Now, there's a guy who wrote a book recently called The Signal and the Noise. And he's quite famous. He's a gambler, and he looks at election data and tries to predict who's going to win. And so we separate. So we're trying to separate the data into the signal, which contains the information, and the noise, that's what's left over. And it's the noise that should be normal, not the data. That makes a big difference. And you can see the difference on these plots here. When we just looked at the cost, which is the data, and did a QQ plot, we got that. But then when we did a QQ plot, and now we use these things called studentized residuals, we probably needn't have done that. We could have just looked at the residuals, the errors, what you get when you subtract the fitted model in statistics, you get residuals. And again, it could be any method where you separate you take away the predicted values, and that's what you get left over. It could be a machine learning method, a neural network, say. Now you see, it isn't the same. You get rather more departure from from the model here at the higher values. So that's telling you something. It's telling you that higher costs have a different shape in a way, and and they could be where these errors occur that maybe need to be fixed. You don't really want that to happen because it might look like corruption. You see, you don't want things to look like that. Well, if there is corruption, you might find it, but it's good to be able to separate out the higher values from the values that are in the using the method. And we understand that there are lower values that are different. This happens all the time. If you actually look at some of these people, the statisticians, like Prof. Karma in Malaysia, who gave a talk at our conference, our SATS conference, he says that the higher values and the lower values are quite different. They have different tails. They have something like Pareto tails, not just even log. So he was saying that the log doesn't fit most financial data, and it departs from both ends. So you see, that's what's happening. Now you can go into that if you wanted to do a bit more theory and stuff. I'll look at things in more detail. Okay, so I just wanted to say that. But now I'm going to show you a plot that probably will take a while to digest. See, we're getting into a bit more complex things here. We're fitting a model where we've got a lot of predictors. We've got, you remember if we go back to the start here, it says the DRGs are determined by primary diagnosis, surgical procedures, comorbidities, and the sex of the patient. You see the procedures, and that includes the identity of the procedure, whether it's taking a pill, which is not much at all, or having a big operation that's very expensive, like a heart transplant or something like that. There's the primary diagnosis, the comorbidities, how sick you are, how many other illnesses you've got. Okay, so now what we looked at, and these were the values that are in the database that you get from the National Health Security Office. You see they have, well, there's the sex, the gender, and also the age. And then you've got the length of stay in the hospital. That's important. Apirity looked at that in her thesis. You've got the primary diagnosis. You've got the deaths, the discharge status. Some of them escaped. That doesn't actually tell you very much. You see, most of them just says no autopsy, no autopsy. Okay, autopsy.
Ajahn Don, could you show the slide, make it bigger?
The what?
Could you show the slide, make it bigger?
Oh, make it, sorry. Thank you.
Yes, thank you.
Is that what we wanted? And then we had to do something else, did we? Is that okay now? Can you see that? Or do I have to do something? Can you see that? No? I had to do something else, didn't I?
I think you need to change the view from presenter view to be maybe, I'm not sure what it's called, but only one screen. But if you have trouble doing that, I think this is okay. We still can see it.
Oh, wait a minute. somehow I've lost the, I'm trying, mouse is sort of not going to the other place.
Ajahn, you go to the top of the screen and go to display setting.
Yeah, but I can't, for some reason, I can't seem to get the mouse over there. Ah, here we are. Good.
Yeah, display setting, yes. And
Okay, now,
so presenter.
that the one?
Yes, that one.
Okay,
Thank
we're
you.
right. Yeah, I can see that I'm going to have to practice a bit more with this because, sorry about that. I'll be better next time.
Okay.
I don't get much chance to practice here, so okay. Well, now we're right. Hopefully. Now, where were we? Yes. Okay. So you can see that all right now.
Yes.
Right. Okay. So we've got, as I was saying, we've got gender and age group. That's a demographic factor. We've got the length of stay, which is divided up into about 12 groups. 0 days, 1, 2, 3, 4, 5, 6, 7 or 8, 9, 10 or 11, 12 to 15, 16 to 24 or 25 plus. And the number of diagnoses is if you look at that, the number of diagnoses seems to be, if you look at the pink dots on that in that panel, in the second one from the right hand side, it looks as if you just put each of those in by themselves into the model and didn't consider the others, that's what the pink dots show. So the pink dots are the crude estimates of the effects. So it shows you that the number of diagnoses is a very good, looks on the surface to be a very good predictor. But when you put in other variables, the effect disappears. Well, the reason for that is called confounding. Now you've got the number of procedures is quite a strong predictor, but that's not a confounder because you can see the pink dots are similar to the black crosses. The black crosses are what the model shows when you put all the data in. This is really quite important, and not many people understand this. Even statisticians that I talk to don't understand it. Even professors of statistics don't understand it. So, don't think that you're not smart if you don't understand this. But it is important to think about it and try and figure out what's going on. Well, the fact is that, and I can show you another slide where it talks about this. Here, you see, here's the confounding. So you read the slide there, the pink points are the crude means, and that suggests that the number of diagnoses is a good predictor of the cost. But this correlation disappears when the length of stay and the number of procedures are included in the model. So it's really a confounding variable. And if you look up on the internet, Wikipedia tells you that what a confounder is. Lurking variable. It's a variable that influences both the outcome variable, the dependent variable, and the predictor variables, the independent variable. It causes a spurious correlation. It appears to be a correlation, but it's not there. Well, looking at all that, you can see that there really are only two predictors that are important. you can see that gender and age group are not really, they only account for, they're not good predictors. They only account for 2.8% of the R squared in the model. And the length of stay is a good predictor because that accounts for 42%. The principal diagnosis is not important. It's only 5%. Now, you see, according to the diagnostic, the DRG theory, that's supposed to be a good predictor of the cost. It's not. So you can just throw that out. They won't, because they believe in it for political reasons, like a lot of things. But according to the study, it's not important. This paper is a very important paper. It'll be famous in time to come, but it's going to take a long time for the medical people to come to grips with it. The discharge status is not important. The number of diagnoses is not really very important. And as I said, it goes away when you put the other factors in. So these R squareds are reduced even further when you put the other variables in. But the number of procedures is quite important. So now we've only got two left. We've got the length of stay and the number of diagnoses, but there's only 12 categories for one and for each, I think, and something like that. And we can reduce the length of stay even more because you can see it's almost a perfect straight line. If you can. So what we do now is we just take the two of them, and they could be correlated with each other. In fact, they are correlated with each other. And so we look at every combination. But that means we've got 72 combinations. We've got 6 groups for the number of procedures. We've got no procedures, 1 procedure, 2, 3, 4 or 5, and 6 to 12. And we've got 12 lengths of stay combinations. So that only gives us 72 parameters. And we've got over 3,000, we've got 3,500 data values. And in fact, we've got 200,000 in the whole data set. And we can still just get just as good if June showed that even with 200,000 data points, you only need 72 parameters to get an R squared of over 70%. That's a very good result. 69% actually. So now we thought, a lot of people think that these machine learning methods like artificial neural networks and random forests are superior to regression. They only are if you don't know much about statistics and you just apply a regression model without knowing how to fit it. If you've got a competent statistician who knows how to use the regression, and I can tell you that we've got quite a few in Thailand, not just the Purity, but a lot more, and not just even in our program. We've got people in other universities in Bangkok and so Chiang Mai and everywhere who are quite good statisticians, and they should be able to do a better job. But you do need a statistician. You need to know something. You need to be trained in statistics. You can't just, well, if you're not trained in statistics, you can throw in the data into a machine learning model And you might do as well. You might even do slightly better, but you won't do more than slightly better than a good statistician. See, here's the results. 60, the random forest method here gives prediction accuracy 69%, which is the same as what you get for the regression model here. And we could have gone further because we haven't put, there's one very important variable we haven't put in, and that's the identity of the procedure. That's whether it's just a pill or, well, a pill would be cheap, but there are expensive procedures that some of them do very well and others don't do so well. So you can look at them too. The type of procedure is, we haven't put that in the model. We've just put the number of procedures. We don't say what the procedure is. That's in the data, but that's a lot more work to put it in, but it still can be done. And that's a good research problem for another PhD student. Okay, so just one more thing. This is just a fact that because you've taken the logarithm, you get a relatively small bias, but there is a bias. You don't get the same result as you would get if you don't take a transformation. I call it a transformation bias. Not many people know. I think economists know about this. Okay, so that's all. I wanted to show you. These are the things you can do with the air pollution data. You can use exactly that sort of method. And just to summarize, okay, in the slide I showed you before, we've got a summary of that. Okay, so there it is. All right, well, that finishes that. Now, the next thing I want to do, if I could get back to somewhere, I want to show you some maps. Get out of it. Okay, where am I? Oh, I'll go to that. Okay, here we are. Now, the maps. To do this, I'm going to have to run R because I haven't made copies of the maps in the slide. I ran out of time this morning. So I'm going to go into R and I'm going to run a program in R, if I can find it. It's in here. It's called, well, we'll start with a map of Europe. We'll start with a map of Asia because Thailand's in Asia. So let's find, okay. It's called Asia Polar. Here we go. Now this is a very dumb program. If my son Ed saw this, he'd say, "Dad, you really need to learn how to program," you know. Because, and I always, he says, "You write too many, your programs are too long." He says, "I can use a function that'll just 2 lines to do all your stuff that takes stuff." But he's right. But I just say to him, "Oh, well, I get paid for the number of lines, so I'm doing okay." Okay, so I'm going to run this program. You can see it gets data for a lot of countries. Where are we? I'll go up to here to start with, just to see if it works. Now we're going to go into R. We do that. Can you see this now?
Yes, we can see, Ajahn.
Can you see what it's doing?
Yes.
You see the map.
It's made a map, and it's put it's put Siberia and China, and it's left out Kamchatka Peninsula. Now you can see that what we've done here. Now Ratikan and I did this, I think, a couple of years ago, and we're using the same grid that Ratikan and I used, but we've got 2 more years of data than we had when I gave a talk in Bogor at a stats conference that they ran there, where I showed a map like this. But this map is even better than the one I showed. And have you ever seen a map like that before? Have you? No. I've never seen one. But I think it's a very sensible map, because you see, when you look at the normal map of any country or even the world as a whole, it uses a projection that makes countries close to the poles look very big compared to what they are. Now, if you look at, if you use Google Earth, say, you can get something very similar to that using Google Earth. But again, it's not the same, because this is better than Google Earth. When you look at Google Earth, it looks okay. When you go, if you show a big area like this, like the whole continent of Asia, it sort of drifts away at the sides where you can't really see things, and it distorts it a lot to the sides. Now, there is some distortion here, but it does better than Google in the sense that it preserves areas exactly. The area of any part on the map is the same everywhere. And the grid is the grid that you make. This is the grid that the NASA satellite makes. When it takes pictures from its satellite of something on Earth, all the pictures are the same size. They're all slightly less than 1 square kilometer. In fact, they're about 0.9, about 0.89, I think, square kilometers. And they're all the same. It doesn't matter where it is on Earth, they're all the same size. And they have to be, because when the satellite takes the picture, it takes the picture immediately of the land immediately below it, which has to be a square. And then it sort of decodes it and gets all the information out, and it actually computes all sorts of things using solar reflectance and solar radiation reflectance, and it gets a very accurate measure of things. For example, land surface temperature, LST. And this is ALST. And okay, and these little circles correspond to those square kilometers. Now, they're much bigger on the map, but I did that because if you put a dot that had a square kilometer of area, you wouldn't see it. It'd be just a tiny thing, because this is a very big area. But the regions separated by the white curves are what are called regions, and each of them contains 9 subregions, where a subregion is actually not just 1 pixel, but 49 pixels in a 7 by 7 square. So they're all together. That's about 42 square kilometers. So each of those little circles is about 42 square kilometers. And I didn't put Kamchatka, but I have put all the rest of the Asian continent, because I didn't want to have more than 99 in each group. And so Northern Asia, which is mostly Siberia, has 99, And then we've got China plus the Koreas plus Mongolia. That's another one. That's 99. Now we've got some more. Let me go a bit further. It doesn't have any islands. Okay, let's get back to the program. Where are we? Oh, I've got to find it. Here it is. Okay, I'll go a bit further. I'll now include the Middle East. Now, the Middle East is not just the Middle East. It also includes the so-called Stan countries, which are former Soviet republics, which escaped when the Soviet Union ceased to exist in about 1990, just before when Gorbachev took over. Okay, there they are. There's Saudi Arabia, Turkey, Iraq and Iran, Afghanistan, and then we go up to Turkmenistan, Kazakhstan, and all the stands, but not Pakistan. Pakistan, I think we got about 81, 72, 81, I think, sub-regions there in what would be 9 regions. And you can see now the next one is Southeast Asia, or South Asia, which includes India and Pakistan. Now the colors mean something. The red color means that the temperature is definitely going up according to the evidence. And by the evidence, I mean it is statistically significant at 2.5%. Right? Now, normally we say something is statistically significant if the probability of it occurring, if that hypothesis were not true, is 0.05, 5%. And so it could be going up or going down. And if it's going up, that's 2.5%, and that's the red. So you see virtually the whole of Siberia is red, and so is Turkey. The pink means it's probably going up, which means the Z value. Now if the Z value is greater than 1.96, statisticians will know that that's statistically significant and going up. If the Z value is greater than 1, but less than 1.96, it's pink. It means it's probably going up, and there's a probability of that of about 1 in 6, about 16%. If it's green, it means that the Z value is between -1 and +1, which means that it's unlikely to be changing. We call that stable. If it's light blue, it's probably going down. And if it's red and there's no red, if it's dark blue and there's no dark blue there, it's definitely going down. So in that whole area, there's nowhere where it's definitely decreasing. So that's global warming. That's why people say that the world is warming. Okay, but there are, when you look at the dots, there are actually some dark blue ones there. You see there? That's a dark blue one down at the bottom I think that's probably in Oman. No, that's in Yemen. And there's another one over here in China. And there's some more in China. And so the orange dot corresponds to a pink region. We had to use slightly different colors to separate them. Okay, I'll go a bit further and I'll get the rest of Asia. Okay. What do you think's going to happen there? Well, now we're getting some dark blue. The whole of India, pretty much, apart from that eastern region, is definitely decreasing in day land surface temperature over that 21-year period. And so is Cambodia, southern Vietnam, and southern Thailand, but not northern Thailand or North Vietnam. You see, so we're getting some different things happening. I remember when Ratikant gave a presentation in Bangkok, and there was a mathematician there. He said, "Oh, what you've done is totally wrong. You're stupid." And told her that he wasn't prepared to listen to her. Well, she was right, because she showed that southern China was not increasing, probably going down. Okay, so and we'll put Europe on. Now we know what's happening in Europe, don't we? Let me do that. I'll just finish it off. So it's almost going up. But since most scientists, I think, are in Europe, aren't they? We haven't got to America yet, or Africa. I'm running out of time. But we've covered the whole world, including Antarctica. We know what's happening. And the map is constructed using a very simple mathematical technique. It's just high school trigonometry, basically. Because, you see, when the people from NASA worked out where the sample, where the satellite was going to go and do everything, they worked it all out using simple trigonometry. They have a sinusoidal projection, which is equal area. Now, it sort of goes wrong a bit at the poles. If you do that to the Earth, you get cusps at the North and South Pole that look a bit funny. They're not flat. But that doesn't matter, because the satellite can't get closer to a pole than about 5 degrees because of the way it goes around in its orbit. It can't go over the North or the South Pole exactly. So we lose. So the only places where we don't have data are within 5 degrees of the North and South Pole. But apart from that, the sinusoidal projection works very well. And so that's what I've just used. What we did, Ratikant actually worked it out, and I got it a bit wrong, but I've since fixed it, and it's even simpler than what we did. All you have to do is convert the latitude. I can show you the code. The code's in the program here. I'll show you the program. Very simple. Here's what you do. You take the latitude, which is X. Sorry, the latitude is Y. That's the vertical measurement on the longitude is X. And then you have I'll go right to the start of the program. You have phi naught and theta naught, which is the point where you want to center the map. So for Asia, we've centered it about there where my cursor is. That is it's at 45 degrees north of the equator and 80 degrees east of Greenwich, which is the primary meridian, you see. So phi naught is minus 80. This is degrees, longitude, and theta naught is 45 degrees north. So we do that, And when we've done that, we then get we've got all the data for the shape files, all these, every country in the world, which is just a simple thing you can download from anywhere. It's publicly available. And then we just, we add phi naught to the longitude, and then we convert it to radians, and we just convert theta to we convert the longitude, we convert the latitude to radians, and then we just take the cosine of theta times the cosine of phi, and that becomes the I call that XC, which is the rotation of which is converting to sort of polar type coordinates, and then we take the cosine of theta and times the sine of phi for the y coordinate. And then the z coordinate, we have a z coordinate as well, which is just the sine, and then we do this conversion back to Cartesian coordinates. There it is, and then we've got it. We've got, and then we just make a polygon with those values. Very simple, and this gives us that. And we can do that for the latitudes and the longitudes and anything else, as well as the boundaries of the countries and the positions of the subregions. Okay, well, I don't know. I think I've run out of time completely now, but if you just give me another minute or so, I'll just show you some confidence intervals. Because you see, when we do this, people want to say, well, what's the evidence? I've made a map, but there's no p-value. Well, it does use p-values, but you don't see them. It just says increase. Well, it puts the z value up there, but no one would understand that. And so we have to say what's the evidence, and a confidence interval is a pretty good way to show that. And they have these things that medical statisticians use called forest plots. When they do a medical study, they want to compare one treatment for cancer, say, with another. They get an odds ratio, and then they make confidence intervals, and they make and so they can do what's called a meta-analysis, where they put together the data from different studies to get a more conclusive result. So I'll show you the confidence intervals for. Okay, here we go. This is a confidence interval for one of these groups. I think we don't show the whole lot. This is just for, this is for North Asia. Well, we know that North Asia is increasing, and actually it's increasing quite a lot. It's increasing by, here's the individual confidence intervals for each of the 11 regions in that area there, which is I call North Asia, which goes around there, goes around to there somehow. Yeah, this is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That one there is the one of them, that one coming down. And there they are, and all of them except the two pink ones, which is that one, the far west one, and the southeast one are, or is it that one? Yeah, no, sorry, that's in Europe. That one, it's the two lower ones. They're just probably increasing. The rest are all definitely increasing, and that shows you that the confidence intervals are greater than 0. The whole confidence interval. These are democratic confidence intervals. They don't have they use the mean as the control group. They don't have any one of them to be the control group. And then you've got, so there's the two is actually one. There must be a. I think there's one that's green. That one there is green, and that's that one there, the mid-south one. Now we can do the same for other parts of the world, and I'm going through and doing that. But I've run out of time. It's now 11. It's now 11 o'clock, isn't it? Your time. So
Yes,
I've used
yes, it is. Yes.
Yeah, but I just wanted to show you this. I'm writing a book actually on all this, and called "The Truth About Global Warming," using data from the NASA satellites. Okay.
Okay,
You're
Ajahn.
scratching your head a bit, thereupon. You look a bit. You were the one who told me I'm sure you were the one who told me that you didn't want to publish any of this in your journal. I should send it to an international journal. Is that right? I think I remember you telling me that about 20 years ago. Okay.
I don't remember that.
Well, maybe I got you wrong. I thought, weren't you the editor of the Sonkanagaran Journal in those days?
I checked with my colleague who ran the journal and asked that if you visited me, and he said that no, we never had the discussion, so I don't recall that. Sorry about that.
Well, it's a long time ago. Doesn't
Yeah,
matter.
yeah. My memory is not very good either.
Yes. Anyway, I'm now that I'm retired and got nothing else to do except do my garden and drive my granddaughter to school and do some shopping and stuff like that. I can focus on writing this book. I'll send you a copy when I finish it. It'll have these maps and things. It's quite interesting, actually. We can sort of show pictures of the places as well. They make the satellite makes very good maps of what's really on the ground. They're all in color. They're beautiful, and they're places you can't get to in any way. You know, the satellite can see things. Okay. Anyway, we're getting away from air pollution. We'll get back to that. You okay, Apurity? You happy with that?
Very much happy, Ajahn. I
Oh,
gain a lot.
You always say that. You're so nice.
Yes, it's very interesting, Ajahn.
Yeah.
I'm not sure anybody have questions. I think if the audience have questions, you can ask. We can spare some little time before
All right.
Professor McNeil leave us, and you will give us the presentation file, right?
Yeah. Well, okay. I can send it to you now.
Or you can share it in the chat. Can you do that?
Yeah, I can do that.
Okay, please.
Let me figure out how to do that.
You may say
I am sharing, so I've just got to chat.
Yes, Ajahn, you go to the chat
here
box.
we go. Chat. Yeah. Now I say to everyone. Now what do? I click on something, don't I?
You click on the.
Here we go. Now, where is it? It's not in COVID. It's in air pollution. It's another folder somewhere. No, where is it?
You may search air pollution.
Wait a minute. I have to go. I have to go up. Look in. I have to go up.
You go to this PC, Ajahn. This PC. You might keep your files in the D drive. This PC, yes. On your left hand side, it is appear the icon this PC.
This PC. Thank you.
Yes.
Now I go
And
to. Well, I'm in C.
you keep the data in your C drive or what?
Yeah, it should be. It doesn't give it to me. Oh, that's funny.
Click on C drive, might be.
You may click on the last button. Yeah, that one, C drive.
Oh, yeah. Click on that, but nothing's happening.
Nothing happened?
Oh, yeah.
Oh,
Oh, here we go. It's an
Evolution.
air prediction.
Yes.
Okay. Is this, it's called, what's it called? This is
Zoom,
it here.
yeah.
So I do that.
Zoom
Yeah.
presentation. Yes. Yes.
Is that going now?
Maybe. Oh, yeah, it's
Yes.
coming.
Yes.
Coming. So the audience can download that. He is very generous to share us the PPT file.
Yeah, it's there. It should be there now, shouldn't it?
Yeah,
Yes.
it is now.
Right.
All right.
Okay.
Thanks a lot. Anybody have questions? The student or the audience? I have one question regarding the data on your air pollution. I think your presentation is very nice, as Dr. Apiyari said. Since I'm not a data scientist and not a very good statistician as well, so my question may be a little bit dumb. If it is, please forgive me. Okay. From the data of air pollution, you see in the time series according to each year. I didn't get it quite because it was quite quick. Since the air pollution in Thailand, in many regions, they are different from season to season. What is the best way to show it? The daily data is not good, right? Because I mean, it's too short of the duration. Maybe the by month or by quarter, or by what is your opinion
Well,
on
I think the weekly data is okay.
the weekly?
Yeah, because if you look, I use the NASA data as a sort of a gold standard, because it's clear that they were very smart the way they planned. And of course, it costs billions of dollars to put satellites like that up. So they have to make sure they get everything right. And their database, their whole engineering, design and everything is really quite superb. And they use an 8-day, when they take a picture, they do present the data every 8 days, but actually the data are not just for one day, because they do a kind of a smoothing. They do very clever things with filtering it, and they come up with this 8-day period. So I think 8 days is a good length of time for something like air pollution as it is for temperature. See, all of these climate variables, and air pollution is another part of the climate. It might be a predictor or an outcome, but so they use 8 days, but that's a week. That's pretty close to a week. I think weeks are better, because you see, a week, if you take it for the week, you completely eliminate the day of week effect. And I think the day of week effect might be quite strong in some places, because people do different things at the weekend. Companies often don't operate at the weekend, or in some sense. So I think a week is the right period to use. and it gets rid of a lot of the correlation, although there's still some left, and it reduces the amount of data you have to worry about. You see, there's only 52 weeks a year, so in a decade you've got 520 numbers for each station, and you can sort of connect it with the variables that the meteorologists and the climate people and already use. So I'd go with a week. That would be my answer, and that takes account of the seasonal effect too. And of course, you can take out the seasonal effect by subtracting and then adding back the mean, just like economists do, where they make seasonal adjustments. It ties in with lots of other scientific methods and engineering methods. So I think a week is a good period to use.
Okay, the reason I ask is that because now we are doing the research on the ultrafine particle in atmosphere, like a nanoparticle, particle smaller than 100 nanometer, or we call it PM 0.1, and that data is not available through any organization. So we use the quite complicated, actually not complicated, but it's a tedious sampling, and it's a static sampling. We have to do it to collect the data maybe 3 or 4 days at a time. So usually we collect it in Hat Yai, and we have done it for 3 or 4 years already with the data. But the data may have available only once or twice a month. So I'm not sure that if we use that data to do the same thing that you done, is it worth?
No,
It's okay.
Yeah, it is okay, because you see, once you've got, even if the data are spaced further apart, you can still fit a model, like a spline model, can be fitted to any data. It can be as wide apart as you like. Of course, if it's too widely separated, there might be some, I don't know, some grouping effects, but it should pick up what's going on. It should be able to pick up the seasonal effect reasonably well, because the seasonal effect is a, you know, the summer, winter, or rainy season, or dry season, or whatever, are more than a week in length. So I think a month would be okay, but it doesn't really matter, because you see what we're doing when, see, I didn't have time to show you this, but when I constructed these curves here, I mean, when I did this analysis, I actually got the result by fitting just a straight line. I just measured the overall increase over 21 years. But one thing that I've also done is to fit a spline function. And one of our students got a nice paper out of this for his PhD, where he looked at the data from Taiwan and he fitted spline models. And the advantage of the spline model is you can forecast, you can look at, see, if you fit a spline function, you might have these knots, which are piecewise cubic, which separate the piecewise cubics. And so you get a more flexible function, which can pick up the seasonal effects. Although usually you fit the seasonal effect and then you take that out, and then you fit a model to the time series that has much wider curves, you see. But you can do all that sort of thing. It's really just curve fitting. That's all it is. So
Okay.
From what you say about the data, it seems to me that that's not going to cause a problem for the method.
Okay. Yeah, thank you very much. อาจารย์อภิรดี are you
So I'm not sure for the student. Any question from the student or participants?
Good morning, Ajahn.
Yes, good morning.
Good morning, everyone. Sawadika. My name is Neni Zulvanengsi. Would I ask something, Ajahn? I'm from
Yes.
Konkan University.
yes please go ahead
You can hear me, Ajahn?
Yes.
Yeah,
Yeah. I
I
just want
can't see
ask.
you, but I can hear you.
I just want ask about the which one application we can use good for analyze the data, Ajahn. Recommendation application.
Well, as you saw, I just used plots of. We started with the box plots, but then but the box plot was really just to display the data. Then when the important result was getting the time series fit. Okay, that's what we're trying to do there, is to separate the signal from the noise, so that we get a curve, which is a time series curve that shows you that contains all the information in the data. And that's what we end up with. And we do that by just subtracting means, really. Very simple. But then the next step, once we've got data on the curve, I didn't talk about this. The only place where I didn't really talk about that at all. But the next thing to do would be to say, you're asking a question about what we should do next. And I did say, I didn't tell you that. I said, it's coming soon. And we're going to be talking about that in the presentations I'll be giving to the graduate students at Princess Songkla University in research methodology and data analytics. Now, if you want to find out what we do there, you should contact Apiridi, and she might allow you to join the Zoom presentations. But it's not something that I could easily cover in this even in this 2-hour talk. I spent a lot of time talking about preliminary things like just getting the data and plotting it, and then I talked about other applications of taking the log transformation, and then I talked a little bit about the maps of the climate data. But I didn't give anything that could answer your question. All I said was that would be the next step, and I know how to do that. Well, at least I'm learning how to do that. I won't say I've got all the answers yet, but hopefully when I start giving the Zoom, the answers will come, and because I'll have to spend some time figuring out what to do. But most of it won't be anything really much new in terms of theory or methods. Virtually all of the methods are there. They're old. Statisticians can't really publish them in statistical journals because they're not new, but they can use them to solve scientific problems, which is what we're really on about. Okay?
Okay, Kak Ajahn. Ofun Kak Ajahn, I'm sorry.
Okay. Any more questions? So if no more question, because we run out of time already, and so this is the important thing of learning from data. Data will tell you what happened in the past. So that's why these are all the things I just don't try to tell you. So this activity actually helped by the Air Pollution and Health Effect Research Center, and the head of the center is Professor Dr. Pirapong Thikaskun. So I would like to invite Ajahn Pirapong to say something to text Ajahn Don, please.
Well, on behalf of the director of the research center at Prince of Songkhla University, I would like to say a big thank to Professor Don McNeil, who is how to say, he is a very special person to PSU, that he come and help PSU for a long time, as he mentioned in the beginning. And today is a very good chance that he give us the lecture on the data for air pollution. And I hope that the audience can understand this and can use it for the future for the research. And if you have any thing that you want to contact Professor McNeil, again, you can either contact him directly or Ajahn Apiladi or me. We can try to contact him. Okay, and I have no more words, but just to say thanks, Professor McNeil, and hope that you can give us the special lecture again in the near future. Thank you very much.
Thank
Thank
you
you,
too.
Ajahn. Thank you very much. So have a nice day.
Okay. Thank you.
Goodbye. Good afternoon or good evening in Australia.
Well, it's afternoon. now.
Afternoon.
Yeah. Well into the afternoon.
Yeah.
Okay. Well, thank you, and I'll see you again, all of you, soon, I hope. Bye bye.
Yeah. Bye, and thanks all the audience that join us, and hope to see you again later.
So
Everyone.
thank you. Bye bye.
Thank you อาจารย์ดอนบ๊ายบายขอบคุณค่ะ
Okay.